Welcome to this lesson on microfluidic droplets as templates for creating advanced materials. Today we're going to explore how tiny liquid droplets can serve as building blocks for sophisticated structures like colloidosomes, porous beads, and anisotropic particles. First, let's understand what microfluidic droplets are. Imagine a stream of tiny water droplets flowing through oil, each droplet perfectly uniform in size, ranging from micrometers to hundreds of micrometers in diameter. These droplets are generated in microfluidic devices, tiny channels etched into glass or plastic. The key advantage is monodispersity. Every droplet is essentially identical in size. Typical droplet sizes range from 10 to 500 micrometers. To put this in perspective, a human hair is about 70 micrometers in diameter. Modern microfluidic devices can generate up to 10,000 droplets per second, giving us massive throughput for material synthesis. Now you might ask, why use droplets as templates? What advantage do they give us over traditional synthesis methods? The answer lies in compartmentalization. Each droplet acts as an isolated microreactor. Reactions happening in one droplet don't interfere with neighboring droplets. The perfect size uniformity means every particle we create has identical properties. This is crucial for applications requiring precise control. The high surface-to-volume ratio in droplets accelerates mass transfer and heat exchange, making reactions faster and more efficient. Let's do a quick back-of-envelope calculation. Suppose we have droplets with a radius of 50 micrometers. How many droplets would we need to synthesize 1 gram of material? The radius is 50 micrometers, which equals 5 times 10 to the negative 5 meters. The volume of one droplet is 4/3 pi r cubed, which gives us 5.24 times 10 to the negative 13 cubic meters. Assuming a density similar to water, about 1,000 kilograms per cubic meter. The mass of one droplet is 5.24 times 10 to the negative 10 kilograms. To get 1 gram of material, we need approximately 1.9 billion droplets. At 10,000 droplets per second, this would take about 53 hours of continuous operation. This calculation shows that while the droplets are tiny, the approach is absolutely scalable for practical material synthesis. Now let's dive into our first material type, colloidosomes. These are hollow spherical shells made from colloidal particles assembled at the droplet interface. Picture a soccer ball structure but at the microscale. Colloidal particles, typically silica or polystyrene spheres, adsorb onto the water-oil interface of a droplet, forming a dense packed shell. The formation mechanism relies on interfacial adsorption. Colloidal particles prefer to sit at the oil-water interface because it minimizes their interfacial energy. The free energy change for adsorption is negative pi r squared gamma times 1 minus cosine theta squared, where gamma is the interfacial tension and theta is the contact angle. The colloidal particles typically range from 100 nanometers to 5 micrometers in diameter. Once the particles assemble at the interface, we can solidify the shell structure through various methods like sintering, polymerization, or chemical cross-linking. What makes colloidosomes useful? Their hollow structure and permeable shell give them unique properties. In drug delivery, the pores between particles allow controlled release of encapsulated therapeutics. The release rate depends on pore size and shell thickness. For catalysis, the high surface area and accessible interior make colloidosomes excellent catalyst supports. They can encapsulate and protect sensitive compounds like enzymes or flavors while allowing small molecules to pass through. Let's calculate a typical shell thickness. If we have a 100 micrometer diameter droplet and use 500 nanometer diameter particles, how thick is the shell if particles form a monolayer? The droplet diameter is 100 micrometers. The particle diameter is 500 nanometers, or 0.5 micrometers. For a monolayer, the shell thickness approximately equals the particle diameter, so 0.5 micrometers. The ratio of shell thickness to droplet diameter is only 0.5%. This shows how thin and delicate these structures are. Our second material type is porous beads. Unlike hollow colloidosomes, these are solid spheres riddled with interconnected pores throughout their volume. Imagine a sponge at the microscale. Porous beads have a continuous solid network, with pores distributed throughout, creating a high internal surface area. We create porous beads by performing polymerization inside droplets in the presence of a porogen, a pore-forming agent. The porogen can be a good solvent for monomers, but a poor solvent for the polymer, causing phase separation. Or it can be sacrificial particles that are later removed. A common example is polymethylmethacrylate, or PMMA, porous beads, made using toluene as porogen. After polymerization, we extract the toluene, leaving behind pores. How do we control the porosity? This is crucial because different applications require different pore structures. The amount of porogen controls the total porosity. More porogen gives higher porosity, but can compromise mechanical strength. The type of porogen affects pore size. Using nanoparticles as porogen creates nanopores, while using emulsion droplets creates larger pores. Porosity, phi, is defined as the pore volume divided by total volume times 100%. Typical values range from 20 to 80%. Let's estimate the internal surface area. Consider a spherical bead with diameter 100 micrometers and cylindrical pores of diameter 1 micrometer with porosity of 50%. The total volume is 4/3 pi times 50 micrometers cubed, which equals 5.24 times 10 to the 5th cubic micrometers. The pore volume at 50% porosity is 2.62 times 10 to the 5th cubic micrometers. If we model pores as cylinders with diameter 1 micrometer, the total pore length is about 3.3 times 10 to the 5th micrometers, or 33 centimeters worth of channels packed into one tiny bead. The internal surface area is approximately 2 square millimeters per bead. This enormous surface area makes porous beads ideal for adsorption and catalysis applications. What are porous beads used for? Their high surface area and accessible pore network enable several key applications. In chromatography, porous beads separate molecules based on their differential adsorption to the internal pore surfaces. The high surface area provides many interaction sites. For heterogeneous catalysis, we can deposit catalyst nanoparticles throughout the pore network, maximizing catalyst utilization and accessibility. Porous beads excel at adsorbing contaminants, dyes, or valuable products from solutions due to their high capacity. Now we come to perhaps the most fascinating material, anisotropic particles. These are particles with directional properties. They're not spherically symmetric. Anisotropic particles come in many shapes: ellipsoids, rods, discs, triangles, dumbbells, and more complex geometries. Each shape imparts unique properties. You might wonder, why go through the trouble of making non-spherical particles? What advantage do they offer? Shape dramatically affects how particles assemble and pack. Rods pack differently than spheres, creating materials with anisotropic mechanical and optical properties. Anisotropic particles can have directional interactions, enabling programmed self-assembly into complex superstructures. We can functionalize different regions with different chemistries, creating particles that are like molecular building blocks with specific binding sites. How do we use droplets to make non-spherical particles? Droplets are naturally spherical due to surface tension. We need clever strategies. Strategy 1 is deformation during polymerization. We flow droplets through constricted channels that squeeze them into ellipsoids while simultaneously polymerizing to lock in the shape. Strategy 2 uses phase separation. Mix immiscible polymers in a droplet. As they phase separate, they form distinct domains that can be locked in, creating Janus or multi-lobed particles. A Janus particle has two distinct hemispheres with different properties. One side might be hydrophobic, the other hydrophilic, making them excellent surfactants or building blocks. Strategy 3 is controlled evaporation. As a droplet containing particles in polymer evaporates, capillary forces and particle packing can create buckled or dimpled structures. Strategy 4 uses microfluidic channels with specific geometries as templates. Droplets flowing through square or triangular channels adopt those shapes during solidification. Let's calculate what happens when we deform a spherical droplet into an ellipsoid. Starting with a 50 micrometer diameter sphere, we stretch it to 100 micrometers long. The original sphere volume is 4/3 pi times 25 cubed, which equals 6.54 times 10 to the 4th cubic micrometers. This volume must be conserved. For an ellipsoid with semi-axis ABC, the volume is 4/3 pi AB circa. If we set A equal to 50 micrometers for the long axis and assume B equals C for a prolate ellipsoid, Solving for B equals C, we get 17.7 micrometers for the minor axes. The aspect ratio is A divided by B equals 2.82. This level of deformation is achievable in microfluidic channels with appropriate flow rates. What can we do with these fancy-shaped particles? Their applications are diverse and rapidly expanding. In display technology, anisotropic particles can have orientation-dependent optical properties, useful for electronic paper and reflective displays. For drug delivery, shape affects how particles interact with cells and blood vessels. Disc-shaped particles can have longer circulation times than spheres. In self-assembly, shape complementarity allows particles to organize into photonic crystals, metamaterials, and other functional superstructures. Let's compare our three material types: colloidosomes, porous beads, and anisotropic particles. Each has distinct advantages. Colloidosomes excel at encapsulation with controlled permeability. The hollow interior provides cargo space, while the porous shell allows selective transport. Porous beads offer maximum surface area for applications requiring high-capacity adsorption or catalyst loading. Anisotropic particles provide directional properties and can be designed for specific assembly behaviors or multifunctional capabilities. What makes the droplet template approach superior to traditional methods? Let's summarize the key advantages. The monodispersity is exceptional. The coefficient of variation, standard deviation divided by mean size, can be below 5% compared to 20 to 50% for bulk methods. The throughput is substantial. Modern microfluidic systems can produce millions of particles per hour in a single device. Parallelization further increases production. The versatility is remarkable. We can template polymers, ceramics, metals, hydrogels, and composites. The structure can be tuned from simple spheres to complex hierarchical architectures. Of course, no technology is perfect. Let's honestly discuss the challenges and limitations of droplet templating. Scale-up remains challenging. While throughput is good, reaching ton-scale production requires either massive parallelization or fundamentally different approaches. Channel clogging is a persistent problem. If particles aggregate or polymerization occurs prematurely, channels can block, shutting down production. Material compatibility can be limiting. Some reactive chemistries or high-temperature processes are incompatible with typical microfluidic materials like PDMS. Cost is a consideration. Precision microfluidic equipment, high-purity reagents, and specialized surfactants add up. This limits applications to high-value products. The field is rapidly advancing. Let me highlight some exciting recent developments and future possibilities. Three-dimensional printing of microfluidic devices is democratizing the technology. Researchers can now rapidly prototype complex channel geometries that were previously impossible. Active control using electric fields, magnetic fields, or temperature gradients allows real-time tuning of droplet formation and particle properties. Multi-step synthesis and segmented flow enables complex chemistries. Each droplet passes through zones with different conditions, building up complexity. Machine learning algorithms are being integrated to automatically optimize synthesis conditions, dramatically accelerating the discovery of new materials. Let's end with a practical economics calculation. Suppose we want to produce 1 kilogram per day of specialty porous beads worth $1,000 per kilogram. Is droplet templating viable? We need to produce 1 kilogram or 1 million milligrams per day. Using our earlier calculation, each 50 micrometer bead weighs about 5.24 times 10 to the negative 7 milligrams. To get 1 gram of material, we need approximately 1.9 trillion beads. At 10,000 droplets per second, this would take about 53 hours of continuous operation. At 10,000 droplets per second per device, one device produces 8.64 times 10 to the 8th droplets per day. We would need approximately 2,200 parallel devices running continuously. This sounds daunting, but for a product worth $1,000 per kilogram, the economics can work. Let's summarize what we've learned about using microfluidic droplets as templates for advanced materials. Microfluidic droplets provide unprecedented control over particle size uniformity and offer scalable production for high-value materials. We can create 3 distinct material types: colloidosomes for encapsulation, porous beads for high surface area applications, and anisotropic particles for directional properties. Applications span numerous fields, including drug delivery, catalysis, separation science, photonics, and advanced materials. While challenges remain in scale-up and cost reduction, ongoing advances in manufacturing, automation, and process integration are steadily expanding the technology's reach. The future promises increasingly complex and functional particles with multiple compartments, responsive behaviors, and precisely programmed assembly properties. Droplet templating is poised to enable the next generation of advanced materials.